So in this video, we're going to be looking at the projections of the PVT surface as shown here. We're going to start off with this projection, and this is termed as the phase diagram, the graph that we see between pressure and temperature. This is termed as the phase diagram, and what we see is basically that previously we were looking at a PVT surface. It was a surface, and now we're representing it on the plane. So on the plane, the surface has reduced to the form of lines now, okay? So there's a couple of things that we need to define here. First of all, let's say if I had my pure substance somewhere on these lines anywhere. Let's say I'm somewhere here. Let's assume that my pure substance is right on this line. So what this line indicates is that there's a certain temperature that exists at which a phase change can take place. So because right now, what is going to happen, like my pure substance exists right on this line, and let's say this process is happening, my substance is being converted from a solid to a liquid, which is melting. So if this is happening and right now my pure substance is right on this line, then I would have a certain temperature that is going to exist at which this phase change is going to be taking place. And this temperature is usually termed as saturation temperature. Okay, it's represented by Ts, let's say. And this would be a certain temperature. I can just identify it by dropping a vertical onto the x-axis. And corresponding to this temperature, I will also have a corresponding value for pressure, which is termed as saturation pressure. And I'm going to get that if I go with the horizontal across that same point. Okay, so these are two things that we need to remember. We have a saturation temperature and a saturation pressure that exist when the phase change is taking place at certain pressures and temperatures. Okay. Then we also have this triple point here. This triple point here designates a point where all three phases, solid, liquid, and vapor, exist in equilibrium at the same time together. So my question to you here is, just pause the video maybe for a second and just try to come up with the answer that what is the triple point of water. Okay, we've talked about this before, or you can go and take a look at temperature scales, whichever book you're looking at, and try to find out that what is the triple point of water. Okay, and come back with that information. That's just one of the things that maybe you will find interesting. Other than that, so we have phases changing on here. So solid to liquid, I'll have basically melting taking place. If I'm decreasing the temperature, I will have basically freezing taking place from liquid to solid. And if I was to go from solid to vapor, then I would have a process which is known as sublimation. And if I was, this is sublimation. And if I was going from my vapor phase to a solid phase, then what would this be called? I'm going from a vapor phase to a solid phase. I'll give you a second. You can pause the video and come back, and I'll tell you what it is. Okay, so now that you're back, it's called deposition. I'm moving from a vapor to a solid. My pure substance is depositing now, so that's why it's called deposition. And now we have, let's say, if our substance is moving from a liquid to a vapor, I would have, because my substance is vaporizing right now, so it's called vaporization. And if my substance was moving from a vapor to becoming a liquid, the opposite way, then I would have condensation taking place. Okay, so that is what the phase diagram helps us with as well. And now I can move on to so the PV diagram, the PV projection off the PVT surface. And on the PV diagram, it really helps us with noticing some of the things here. Again, I have this critical point here, which joins the saturation line. Okay, this is the liquid saturation line because I have my liquid in this region. And this is the vapor saturation line. Okay, so these two join up at the point which is known as the critical point. And an important thing to note on this PV diagram is that we also have these lines running on this graph. These are the constant temperature lines. So these are isotherms on the PV diagram. Okay, and this line indicates basically the temperature line for the critical point, so Tc. And there's one important thing that we need to consider here, that when our temperature of the substance is less than the critical point temperature, what we have is that we are moving along here smoothly towards this dome, and as we reach the dome here, the pressure becomes constant. Okay, so the pressure here becomes constant for the same line, and we move horizontally. So what this means is that if I had, let's say, a temperature that is less than the critical temperature for my substance, and I had a certain specific volume, and now if I reach this point, I will not be able to basically increase the pressure for my substance until I get to this point here. Okay, I mean, what I mean is that this can't happen, that I reach here, now I'm in the middle here somewhere, and now the pressure starts increasing from here. This cannot happen. I would have to go all the way until I reach the liquid saturation line, and then from here I'd be able to increase the pressure once my substance has been converted into a liquid. And when I'm within this region, within this dome, my substance is going to exist as a two-phase mixture, as a liquid and vapor mixture. So let me just review this again. Let me erase all of this. And so we have a critical point here at which the saturation lines join together. Over here, we have the liquid saturation line, okay? And over here, because this is towards the vapor side, so this is the saturated vapor line, okay? This is the saturated vapor line. Let's call this Vs and Ls. And now, if let's say the temperature of my pure substance is greater than the critical temperature, then I don't really even get to go towards the liquid vapor region. Okay, then I stay within the vapor region. But if my temperature is less than the critical point temperature, less than the critical temperature, as suggested here, okay, then what happens is that I can keep on, let's say, decreasing the volume, okay, decreasing the volume by increasing the pressure. So if I have to decrease the volume, then that means I have to go in this direction. And to decrease the volume, I need to increase the pressure. So let's say I'm increasing the pressure now, and that means that I'll be moving on this curve, okay? And I'll keep on moving until I get to this point. on the saturated vapor curve. When I get to this point, I cannot increase the pressure anymore. Okay, I cannot directly increase the pressure anymore. I would have to go through this liquid vapor region. And in order for me to do that, now my pressure would have to remain constant. I would move through here until I get to the saturated liquid line. Once I get to that, then let's say my pure substance, water, let's say, my water is now completely liquid at this point. And now I can increase the pressure off my substance. There can be a lot of lines over here that can keep on doing this. Okay, I can reach here at a lower pressure. And then I would again have to move on a horizontal line until I get to this point, and then I would have to move upwards. Okay, so the line within the liquid vapor region, that is going to remain horizontal every time. Okay, over here there's not going to be any change in pressure. The only thing that is changing here is specific volume. The temperature is constant, whatever that temperature is, less than the critical temperature. The temperature is constant within this region. The pressure is constant within this region. Only the specific volume is changing. So over here, let's say the specific volume is going to be some value V1. And by the time I get to this other end, the liquid saturated line, I would have a lower specific volume. Okay, and now I'd be able to increase the pressure. So these are the phase diagrams and the PV diagrams for a substance that expands on freezing, like water. And just like this, we would have PVT surface for substances that would contract on freezing as well. The way that you would see the PVT surface is going to be different. It's going to be a different PVT surface for a different substance. You can go ahead and think of an example for a substance that contracts on freezing. I'm going to just go ahead and show you the projections of what the phase diagram and the PV diagram for a contracting substance would look like, a contracting substance when on freezing. Again, there's going to be some changes in the way these lines are being represented. So for example, for the substance that expands, you would have this solid liquid line, which would be tilted towards the left a little bit. Over here, it's tilted towards the right. So you would have some of these differences depending on the substance you're looking at. So for each substance, you will have, let's say, a varying diagram, but we usually constrain ourselves to talking about substances that expand on freezing, so that they would have similar PVT surfaces, and then substances that contract on freezing, they would have similar surfaces. But when it comes to problem solving, we usually stray away from the phase diagram and the PV diagram, because what helps us more with our analysis is actually a TV diagram, okay, temperature specific volume diagram. So in order for me to explain this diagram, let's just consider, let's say, a closed system that has a unit mass. So a mass of 1 kg, let's say, of liquid water. So we have, let's say, a liquid water over here. And this is the piston cylinder arrangement. So this is a piston on top of it. And we're looking to basically expand this liquid water, or basically convert it from a liquid phase into a vapor phase. Another thing that I should mention here is that during our discussion, we're only going to be looking at 3 phases: the liquid phase, the vapor phase, and the 2-phase region, which is the liquid vapor phase. Okay, so these are the only 3 that we're going to be looking at. We're not going to be looking at the solid phase over here. So we have this water that exists at 20 degrees of temperature, okay? And that's also being shown on the diagram here. So I'm looking at state 1 right now, the initial state. Okay, it's at 20 degrees, it's in a piston cylinder arrangement, a unit mass, so a mass of 1 kilogram. And what other data do I have? Okay, so now I'm gonna assume that I'm providing heat to this water. Okay, so heat transfer is taking place, keeping the pressure, let's say, I'm slowly heating the water, its pressure is being kept constant and uniform at, let's say, 1 bar over here. Okay. So now that I'm over here at 20 degrees of temperature, it would have a certain specific volume here too. Let's call it V1. And the temperature is 20 degrees. Now what is happening over here? This is the saturated line that we were talking about, the saturated liquid line. So whatever is to the left of the saturated liquid line, that is usually called a subcooled liquid. Okay, subcooled liquid. Over here, this region, this entire region is called the subcooled or compressed liquid region. Okay, because the temperature over here, the temperature at these states is less than the saturation temperature at the given pressure. Because what is the saturation temperature? The saturation temperature is whatever temperature we're going to have at the dome, at this curve. Okay, so whenever we have lower temperature than this, which it is right now, because the saturation temperature right now is 100 degrees. This is the saturation temperature. Okay, so right now our temperature is less than the saturation temperature, so we are within the subcooled or compressed liquid region. So the name liquid, subcooled liquid, compressed liquid, all of these names are used interchangeably. And now let's say that I'm increasing the temperature, so I'm providing heat into the system, and that means temperature is increasing. When the temperature of the system is increasing, that means I'm going to be, because I'm keeping the pressure constant, remember, and these are constant pressure lines that you see here. This is a constant pressure line. This is a constant pressure line. And so is this one. So I'm moving on a constant pressure line from 1 to F until I reach F. And when I reach F, now I'm at the saturated liquid state. This is state F now. So I was at state 1. Now I'm at state F. Let's keep track of the processes too. So right now I've accomplished process 1 to F by providing heat to the system, by increasing the temperature. I've accomplished a process 1 to F from state 1 to state F. Okay, that is the first process. Now I want to basically, because the purpose is to convert this liquid into a vapor. So that means I would have to go through this two-phase region, which is going to be the liquid vapor region. So again, looking at the same diagram. Okay, this is the same diagram. Okay, so until here. And now, because the temperature has increased, and because the specific volume is increasing too, so the volume is increasing. So I have more volume in here. Okay, but now, when I'm going to be moving within this region, when I start moving from the state F, okay, there's not going to be any change in temperature anymore. The temperature is going to remain constant. The pressure is going to remain constant too. I'm supplying the same pressure. I'm still supplying heat. I'm still supplying heat, so the temperature is still there. Now the temperature is going to remain constant, but what is going to start happening is that instead of staying at state F now, this liquid water here is going to start becoming a mixture. Now it's going to be liquid plus vapor in here, okay, together, mixed in together. It's a mixture right now. So now we have a two-phase liquid vapor mixture in this piston cylinder arrangement. And when a mixture of liquid and vapor exists in equilibrium, the liquid phase is a saturated liquid and the vapor phase is a saturated vapor. Okay. So if the system is heated further until every last bit of liquid has vaporized, it takes us to this point G. Okay, so we have arrived at point G now. And now what you can think of is that how are we going to distinguish that where are we on this line? Like what gives us the information that either we are here at this point or either we are here at this point. So this is something that we conclude we draw this conclusion from something called quality. Okay, so quality of the mixture indicates that where are we on this line. Okay, and quality is represented by X, symbol X, and we can just basically define quality in terms of the ratio of the mass of vapor that is present to the total mass of the mixture. Okay, so the total mass of the mixture is going to be equal to the mass of the liquid plus mass of the vapor, and quality is just the mass of the liquid that is present in the mixture. Okay, so the value of quality here ranges from X is equal to 0 until 1. So a value of 0 means that our mixture is completely liquid, okay, because no vapor mass exists. And a value of 1 means that our mixture is completely vapor. And in the middle, if we are closer to 0, we are going to be closer to this point. If we are closer to 1, we're going to be closer to this point. So if, let's say, you have your quality is 0.9 something, you're going to be probably somewhere close to here. And if your quality is 0.1, you're probably still somewhere here. Okay, so quality is the one that determines that where are we on this liquid vapor mixture line. And now once we have reached at this point G now, okay, so let's call this F to G. Okay, so we have reached point G now. This was 1 to F was where we had the liquid state. F to G is where we have the two-phase liquid vapor mixture. And now when I've arrived at G, now when I start heating it further at the fixed pressure, what's going to happen? My pressure is still fixed. Temperature is going to start increasing, but after my phase has been converted into a vapor completely. Okay, so I have a vapor now here. And this is called the region over here. This is called the superheated vapor region. Okay, because let's say I've arrived at state S now, whatever the temperature is higher, and I have a higher specific volume too, pressure is constant. So the superheated vapor state of the system is referred as such because the system would be at a temperature that is greater than the saturation temperature. Okay, so saturation temperature is constant within the two-phase region. Over here, it's still at the saturation temperature. And in the superheated vapor region, our temperature is higher than saturated temperature. Okay, so these are the three things that we are looking at from 1 to F, which is the liquid state, from F to G, which is the two-phase liquid vapor region, and then from G until S, which is the vapor state. Okay, so this is how you move on the TV diagram. Remember that the pressure remains constant, a horizontal line on within the two-phase region. Okay, we have a TV diagram. Okay, temperature on the y-axis, specific volume on the x-axis, and then we have isobars that are being represented by these lines that are run with constant temperature lines. Sorry, constant pressure lines. Okay. So now what you should notice is that we can go ahead and find out the values of temperature and specific volume and pressure for our substance, let's say water, through this TV diagram. But uh, it doesn't really give us any information about if, let's say, we wanted to find out the internal energy of the system at these temperatures and pressures, or if we wanted to find out the enthalpy, um, or if we wanted to find out, let's say, the entropy of our system at these states. Okay, so because we want more information, it's easier for us to uh, go ahead and take a look at thermodynamic tables. So what I would recommend is that before we move on to the next video, you go through tables A-2 until tables A-2 until A-6. At the end of the book, at the end of Shapiro's book, it's Shapiro's book titled Fundamentals of Engineering Thermodynamics. So just move at the end of the book, go to the tables in SI units, go from table A2 until A6. These are called steam tables because these give us the properties for water, and just go through them and see and have an idea of how this temperature, pressure, and volume information can give you and information for these three as well. So that is what we're going to do in the next video. We're going to find out the values through steam tables, how steam tables are used. Okay, that is what we're going to be doing in the next video.